I'm going to present some work on evidence for radiative-convective bistabilities in tropical atmospheres that I've been doing with Colin. And Daniel's talk was a perfect setup for this because I'm basically going to talk about all the ways that OLR is not linear. So in general, obviously, he's right. When you heat up the planet, energy balance requires that we also increase OLR, and everything at the top of the atmosphere works out nicely. But I'm actually going to talk about a couple of phenomena where this doesn't actually occur. And the first is something that we can observe in the Earth's tropics. It's called the super greenhouse effect. The second is something from planetary science you've all heard about lots this week, which is the runaway greenhouse. And I'm sort of going to connect these two with some predictions that have been made with radiative-convective equilibrium models that see some bistabilities for moist atmospheres. So first, a little bit of background on all of these things. The super greenhouse effect is basically a really enhanced water vapor feedback in the upper troposphere that we can see in some tropical areas of the Earth's tropics. Actually, at any given snapshot, quite a lot of them. And it basically results in, we actually see decreasing OLR with increasing surface temperature because we have so much moisture high aloft that it's like Daniel was saying, absorbing a lot of OLR, and we're seeing OLR from cooler levels aloft. And this is a source of a lot of the excess heat that builds up in tropical atmospheres, which drives lots of phenomenon like extreme precipitation and convective storms. I won't talk too much about runaway greenhouse because we've heard a lot about it, but safe to say it's sort of like a possible end state of moist atmospheres. Once the atmosphere is totally saturated and water vapor is a major constituent, there's a limit on OLR that planet can emit. And if we absorb more solar radiation than that OLR, we're going to have runaway surface temperatures. And there's been some papers in the past, Pierre Humbert in particular, where he pointed out that the Earth's tropics are actually near surface temperatures where we see runaway greenhouse conditions initiate in models. So this led us to think, well, maybe it would be a good idea to look at the Earth's tropics and see if they can give us an idea of how we might transition to a runaway. And I'm going to tie these two concepts together using some or inspired sort of by some work that has come out of models of 1D radiative-convective equilibrium. So this is from a paper by Nilton Reno. And he found that instead of using, if he didn't use prescribed relative humidity, but rather an active hydrological cycle in his 1D model, he got two possible stable states for his moist atmosphere. So rather than just an increase, one stable state and then a runaway, there's two distinct ones here. So I'm going to use a little bit of satellite observations of the Earth tropics and also some 1D modeling that we did and tie it all together with this bistability. So first, just a quick overview of where the data comes from. It's from two instruments on board a NASA satellite Aqua. All the data that you're going to see in this talk is daily means, 1 degree by 1 degree grid. And we're going to look at specifically columns over the tropical and subtropical oceans, so not over land, because we want to know about things that are moist and hot. A little bit about the model. It's a radiative transfer model called SMART. All the results here are going to be for clear sky conditions and surface albedo of 12%. We're going to include a small collection of greenhouse gases, and we're going to parameterize water vapor with constant relative humidity throughout the column. So the first set of results. This is observed clear sky outgoing long wave radiation for the columns that I talked about earlier. On the left, we have OLR as a function of surface temperature. On the right, we have total integrated column water vapor. The red dashed lines are the means, and on the left, these contours correspond to measure column water vapor in 5 kilogram per meter squared segments. On the right, these contours are the column water vapor from that constant relative humidity that we put into the model. So you can see there's this linear trend that we saw in the previous talk, But OLR actually peaks for these kind of columns once you reach a surface temperature of 298 degrees Kelvin, and then it decreases on average for higher increases in surface temperature. So this is an unstable situation, all the way down to 278 watts per meter squared at the highest temperatures that we're measuring. And you can see that this is the super greenhouse effect right here coming into play. And you can see it's preceded by a sort of rapid moistening of the column. That's where these contours become really narrow. And that's also where this part of the plot becomes really steep. Oh, I didn't mention that the color background here is an indication of data density, but at each given surface temperature, so not like over the whole plot. Actually, one more thing. Something that's really interesting is that the super greenhouse is bringing down OLR to really close to the runaway greenhouse limit. So we know from previous calculations that's 282 watts per meter squared or thereabout. And so maybe this super greenhouse effect could give us an indication of how a runaway greenhouse might initiate. Is this sort of the onset of runaway conditions? And to answer that, we're going to use our model, and we're going to take a look at the optical depth of the troposphere. So in a runaway greenhouse, like Daniel was saying, the optical depth of the atmosphere, the troposphere becomes optically thick. So what happens is you have so much water vapor in the atmosphere that it's absorbing all of the thermal radiation from the surface. So if that were happening under a super greenhouse, we would see emissions from some cold level aloft in the troposphere. We wouldn't see any contribution to OLR from surface emissions. And so this is the same plot you saw from the previous slide. The colored part is our satellite data. And then these curves are the results from our radiative transfer model with increasing relative humidity from 20 to 100%. And the little black circles, which are hard to see, I'm sorry, are where those model curves intersect the mean. And they also correspond to these plots on the right. So this is a plot of the altitude where emissions are able to reach space. So this gives us an idea about the optical depth in the model. And if we were in a runaway greenhouse, we would see that the surface would be totally cut off from emitting to space. But what we actually see, these four on the bottom are the ones that correspond to our measurements. We actually see significant surface contribution in the water vapor window. So that's like between 8 and 14 micron down here, except at the very hottest one where we have quite a large contribution from up in the atmosphere. And this is why we're not seeing an OLR that linearly corresponds to the surface temperature. But there's still a lot of surface contribution. So we can pretty confidently say that super greenhouse is not leading to a runaway, which is nice for habitability for sure. But we want to take a look at, okay, well, if the troposphere is not becoming optically thick, what's going on? Well, we can see that the boundary layer is probably becoming optically thick. This is a plot of downwards minus upwards thermal flux at the surface. So down here, where it's nice and cold, we have a lot of upward thermal flux from the surface compared with downward thermal flux from the bottom layer of the atmosphere. But really quickly, those two things become equal, right around the same temperatures where super greenhouse is happening. So what's happening here is the surface and the atmospheric layer right above it are becoming basically the same temperature, and that atmospheric layer is optically thick. So now we need another mechanism besides radiation to dissipate heat from the surface. And what we get is dynamical movements, we get convection, we get moving of that moisture off. And that's what initiates our super greenhouse effect. The troposphere is not thick. So if there's two different physical phenomenon that are dictating the super greenhouse and the runaway greenhouse, we can reconstruct the bistability diagram we saw earlier and take a look at what the transition to a runaway might look like. So this is our mean clear sky OLR that we measured from the tropics. And these are from our model runs. This little blue line just extends this trend downward because the measurements don't quite intersect with this 100% curve. And what we can see is that the super greenhouse effect functions, oh, that's counting down. Okay. The super greenhouse effect functions as an unstable regime that is connecting this stable linear curve where we're subsaturated with this stable curve where we have a totally saturated troposphere. And so I think that the existence of the SGE and the fact that we can measure it like this gives us a good reason to believe that this bistability will exist for moist atmospheres. And this is typically known as something called the moist greenhouse state. So this is all fine and dandy, but you might say, hey, Maura, have you looked outside this week? It's really hot and it's really moist and it's certainly not cloud-free like all of this data. And I will say, don't worry, I did look outside and I thought about that. And so this is what it looks like if you include all sky measurements. It's a bit more complicated, so I'm not going to spend too much time here. But basically what happens is you increase cloud fraction, you amplify the super greenhouse effect, so it becomes stronger. You actually decrease OLR quite a lot more. So down here, this black curve at the bottom is when you have 80 to 100% cloud coverage, and you can see OLR is generally decreased everywhere, but the super greenhouse effect is really strong. Clouds are also reflective, though, so they have an influence on co-albedo, and that decreases too, but not as much. So in general, we can say that in this regime, clouds are destabilizing and they amplify the super greenhouse effect. And with that, I'll leave my conclusions up here. Thank you very much.
Thank you very much, Maura. And now we have a couple of questions.
Very interesting talk. On your penultimate slide with the clouds, doesn't that behavior also depend on the relative contribution of high and low clouds?
Oh yes, it totally does. And I haven't dissociated two in this plot. This is just total cloud fraction. So it would depend a lot on which kind of clouds you're going to get. But the fact that clouds amplify the super greenhouse has been also found in a couple of GCMs that are looking at the transition to a moist greenhouse. So in general, clouds are destabilizing at these surface temperatures and then stabilizing once you get to the saturated regime. So I think this is probably, at least a first order, a correct result.
Right, thank you.
Yeah, no worries.
The idea that the super greenhouse initiates because the surface can't radiatively cool anymore is, in theory, you could test that because it would mean that the super greenhouse should initiate faster in regions where the surface mixed layer depth is shallower.
Yeah,
so is that actually the case? Like, for example, in the real world, the mixed layer over the Gulf of Bengal is way shallower than somewhere in the middle of the Pacific. So is that actually the region where you see the super greenhouse kicking off?
So I wanted to maybe include a plot of where you see super greenhouse, but I had a lot of slides and didn't have the time. You do see a lot of super greenhouse in places like the Pacific Warm Pool, for an example. And one thing that we're going to do in the future is try to take a look at a lot of radiosonde measurements in those areas. So we can pretty easily pick out super greenhouse from satellite measurements like this, and then go in a lot more detail to those stations and take a look at what the atmospheric profiles look like. That is not something that I've done. I think would be really, really informative, for sure.
Well, so one thing I'm a little confused about is if you, when you find observations in the super greenhouse state, even though it's unstable. And so I was wondering if you think that's because it's being restored by adjacent regions, and if that means if the whole tropics got to a temperature where it reached the super greenhouse state, would you expect to suddenly shift by 20 degrees, warm by 20 degrees?
Yeah, that's a good question. So you're right in that because we're looking at only clear sky measurements, a lot of these in the super warm areas are at sort of subsistent regions around large convective cells. And you can kind of see that in like the first figure here. So you'll notice that column water vapor doesn't just like continue to accelerate in these clear sky columns. And that's because when we're looking at measurements like way up here, most of the super warm and super moist areas of the Earth's tropics are no longer cloud free at that point. So we're sort of like sub-selecting a bit of a weird sample space there. In terms of whether or not the whole tropics got to that temperature, what would happen? Yeah, I think you would have pretty different dynamics going on. So there's a really good, I think it's Wolf and Toon 2015 paper, where they try to transition a GCM into a moist greenhouse. And what they see is sort of like the general circulation in Hadley spread out, and you start to see like a lot of clouds in the subsistence region. So I think that you would start to see this cloud effect dominate a little bit more. I'm not sure how the instability would work, so what the transition would look like, whether you would still have enough dry regions to transition yourself back to the stable branch, or whether it would jump forward to a moist greenhouse. I don't know exactly what the dynamics would look like in that zone. Yeah.